Yes, good morning, students.
Good
Good
morning,
morning,
sir.
sir.
Good morning.
Sir.
Thank you. Okay. So before I take up the next topic, just let me have some questions. Okay. Uh, Teja, can you just tell me what are the key enabling technologies for LTE?
Yes, sir. OFDM,
Okay.
orthogonal frequency division multiplexing,
Very good.
SCFTE, FTMA,
Okay.
channel dependent multi-user resource schedule,
Very good.
multi-antenna techniques,
Yeah.
IP-based flat network architecture.
Very good. Very good. So these are the five key enabling technologies we have discussed, right? So far. Okay. Uh, yes, Shuvas Reddy, can you just mention a few advantages of OFDM?
Sir, no interferences, sir. Interferences can be avoided.
Okay, so OFDM can minimize the intersymbol interference. Okay, fine, very good. Yeah, then
Uh, that's it, sir. I know.
that's all. Only one you have remembered because I might have told around 10, around 10 advantages. Okay, why we select OFDM? What is the choice? Why the OFDM has been selected for LTE?
Sir, high data rate, sir.
No high data rate. No. First
Like the
one is
symbol,
fine.
symbol
Yeah.
time is shorter. That's why high data rate, sir.
Mm, no, no, that may be correct, but not very specific. You have to tell like first one you said no, it can minimize or reduce the multipath interference or intersymbol interference in that line.
Yes, sir.
Okay, I will ask somebody else. Yes, what about Pranav?
Yes, sir. So, OFDM has reduced complexity, sir, because
Yeah.
it's implemented using fast Fourier transforms.
Okay. So to put it in a proper way, you have to say reduced computational complexity. Computational complexity, how to tell? Just not just complexity. Okay. Reduced computational complexity because of the use of FFT and IFFT. Okay. Yeah. Then what else?
So, and it can degrade properly under excessive load. When you say
Okay.
excessive
The
load.
degradation of the performance of OFDM happens slowly, not drastically, right?
Yes, sir.
Okay. Yes. What about Ritika? Yeah, Suhas Reddy has told one advantage, then Pranav has told another two. I think
Sir,
I
she has a
expect you
meeting,
to.
it seems, sir. Internship meeting.
Ritika is in meeting. Okay, simply logged in here. Okay, fine. What about Sonali?
So it's spectrally efficient. That means the subcarriers won't interfere with each other.
Okay, it is spectrally efficient. Yes, anything else other than that?
Uh, Also,
Hmm.
there will be high bit
Uh,
rate applications for it. So
hmm. Yes, what about Deepak Tiwari? Deepak Tiwari. Yes, Deepak Tiwari is not there. What about Chandan?
Sir,
Yes. Can you mention advantage of OFDM, man?
I was absent last class, I guess.
Okay, that is fine. You may be absent, but nothing wrong in reading and understanding, na? You
But
cannot, that I
I
won't
haven't
expect.
read, sir.
Whether you are present or absent, you should have the knowledge of the topics, whatever I have taught. You cannot code that I was absent. Yes, Saujanya.
Sir, so this inter-symbol interference which is caused by multipath.
No, already that is told, na? Told by Suhas Reddy. I expect you to tell other advantages.
So multi-carrier modulation they can be overcome by. Multi-carrier modulation technique can be overcome by.
So not specific. Yes, what about Dharma? See, this is a compulsory question will come. Okay, advantages of OFDM. For 8 marks they will ask. Around 8 points are there. What is this? Taking 6, 7, 8 hours of class and stressing more upon these issues, right? And deliberated properly. Even then, people can't just mention the name. I'm not asking to say in depth, just in one word. Okay, this is the advantage. This is the advantage. Yes, Dharma.
Sir, suitable for coherent demodulation.
Okay, suitable for coherent demodulation. Very good. Then, yes, what about Aman Sharma? Aman Sharma. Yes. Yes, I expect you to tell any one advantage. Okay, Reddy has told
Yes, sir.
Yeah,
Sir, it's robust against narrow band.
narrow band what? Robust
Narrow
against
band
narrow
frequency.
band interference. Okay.
Since such interferences affects only a fraction of subcarriers, so it is
Okay.
robust against them.
Okay. Fine. Yes. What about Madhura? Yes,
Yes, sir.
Madhura.
Yes, sir. Yes, sir.
Yeah. Can you tell one advantage of
It is
OFDM?
efficient support of broadcast services.
Okay. So efficient support of broadcast services. Fine. What about Meghana? Meghana.
Yes, sir.
Yeah.
It facilitates
Hmm.
use of MIMO, sir.
Yeah. It facilitates the use of MIMO. Very good. Then what about Gautam?
Sir, it makes efficient use of spectrum by allowing overlap, sir.
So you can say exploitation of frequency diversity. Okay.
Yes, sir.
Okay. So around 9 to 10 advantages I have mentioned. Okay, more or less I could get from each one of you, but it is a definite question for your uh, exam. Okay, they will ask you the advantages of OFDM and these key enabling technologies. Okay, that is network architecture and other things. So you have to be thorough with the first part of module 1. See, next part, that is in module 1 only, another part is about basic concepts of wireless cellular concept, then about the channel. So I will be taking that uh, in a superficial manner because I cannot go so depth. But whatever I take, those will be important for understanding of the further topics. That is why I would like to throw light upon each and every term of the second part of the model 1 also. Okay, whatever I thought so far, if you read, you will be able to answer one full question. If you're pakka with the topics, whatever I thought so far. Okay, so don't think that the second part you need not read, but it is required. It is required to understand further modules. Okay, otherwise it will be meaningless. Okay, if I say frequency selective fading or flat fading or path loss, shadowing, all those terms. Okay, fine. So with this, let me begin the today's class. So that is the about cellular concept. So this is very basic. Hope you will be able to see the slide. Yes, hope you are able to see the slide now.
Yes, sir.
Yes, sir. Yes, sir.
Yeah. Okay. Yeah, I think I minimized it. Yeah, fine. So to understand how this cellular concept has evolved, okay. So let us assume that there is one base station, okay, right? So with it can transmit high power. So usually I said the base transceiver station, right? BTS will be able to transmit the power, and as well as it can receive the signal, right? So if with a high power, it can cover say 30 kilometers or even 100 kilometers. Let us assume, okay. And with that, we all know that the spectrum is a very scarce resource, and it is limited also. So it is possible to accommodate only few number of subscribers or users, what I can say. Okay. I hope you understand with the first diagram. Single cell with high power transceiver. Okay. So with this, we will not be able to provide a service to the many number of subscribers, and also we know that the frequencies or spectrum is a very limited, scarcity or scary resource, so which need to be utilized as efficiently as possible. Okay, to use the spectrum as efficiently as possible and accommodate more number of subscribers. So the cellular concept has come into a picture. So what we do here is we are replacing this single high power transmitter with low power small transmitters. Each will be providing a coverage only to small portion of the service area. I hope you'll be able to see the second diagram. So multiple cells with low power transceivers. Okay, so that area only will be covered by many base stations, right? So we are here uh, reducing the power. Okay, by reducing the power, we will be able to reuse the frequencies. So here the concept of frequency reuse played a very important role in utilizing the spectrum as efficiently as possible. And whatever the frequencies we are using in one cell, the same frequencies will not be used in the neighbor cells, okay, or in the adjacent cells. So the frequencies used in the adjacent cells will be of different frequencies. Fine. So each base station is allocated a portion of total number of channels available to the entire system. And as I said, the nearby base stations are assigned different groups of channels, so that all the available channels are assigned to a relatively small number of neighboring base stations. So with that, what happens when I am assigning different frequencies to the neighboring base stations, I can avoid the interference. Okay, interference between the neighboring cells is minimized. So here we need to understand the with I have shown the first diagram with a rough structure, right? So it is actually the coverage will be like this, but for mathematical analysis, we have taken the shape of the cell as the hexagon. Okay, so it simplifies the mathematical analysis. And but idealized shape of the cell will be like this. It will be covering in an omnidirectional in all the directions. Okay. Okay. So this cell size can vary from as small as to say of around 100 meters up to 35 kilometers. So that depends on the user density, geography, and as well as transceiver power. Okay, so maybe in rural areas, so we use the high power transmitter so that it can cover certain villages, and there the number of users will also be less. But in urban areas, the population is more, so more number of subscribers will be there. That is why we will be using what small cells. Okay, that is with less power, we will be covering the entire geographical area by more number of base stations. So with that, we will be able to cover the entire urban area with a few number of frequency bands. Okay, and here when the mobile user is moving from one cell to another cell, is called as to be handed over, right? So handover of the connection to the neighboring cell is also an important part of the cellular concept. Okay. So as I said, the service in case of means to say about the cellular concept. Okay, the service area is subdivided into smaller geographic areas that we call as a cell, and each cell will be served by their own base station. Okay. So as I said, to minimize the interference between the cells, the transmit power level of each base station is regulated to be just enough to provide the required signal strength at the cell boundaries. Fine. Okay, so here I have shown here. This is one cluster, what we say. So 7 cells are there, right? A, B, C, D, E, F, G. So this we call as one cluster. So whatever the, and I'm going to replicate that over the other geographical area. Okay, hope you're understanding what I'm saying. So cluster means group of cells, right? Here I have used a cluster of size 7. Okay, 7 cells I'm using. So cell A, B, C, D, E, F, G, all these 7 cells will be using different frequencies. So they will not be using the same frequencies. So certain band is allocated. In that, certain number of frequency carriers are available. All those frequency carriers will be distributed among these 7 cells. Okay, and the same thing will be replicated for another geographical area. So like that. Okay, so that it can cover the entire geographical area. Is that fine? Hope you got my point.
Yes, sir.
Yeah. And we all know that the propagation path loss, okay, allows for the spatial isolation of different cells operating on the same frequency channels at the same time. I will come to this. What is path loss? How do we calculate? Right. I think as of now you may be aware. As we move away from the base station, the powers received by the receiver will be decreasing exponentially, right? So that makes us to spatially isolate the different cells, okay, which are operating on same frequency and at the same time. That is what the understanding is here. So with that, we will be able to use the same frequency channels, right, which can be reassigned to different cells. So as long as those cells are spatially isolated, means here see I named no A. Okay, whatever the frequencies I'm using in a cell A, okay, the same cells, the same frequencies will be used in another cluster, which is named by a cell called A. Okay, so we call these are co-channel cells. Okay, the cell named by B will be using the same frequency channels in this cluster also. That is why it is named with the same letters A, B, C, D, E, F, G. Again, it is also A, B, C, D, F, G, A, B, C, D, F, G, right? The cells which are named with the same alphabets will be using same set of frequencies, same frequencies. That is why we call them as co-channel cells. Okay, so let us see what is the difficulty and all in the subsequent slides. But so I said no, the frequency reuse, right? So if they are because of that propagation path loss, we will be able to reuse the frequency, right? So if I say the frequency reuse factor is less than 1, okay, that has to be less than or equal to 1, and if it is 1, means all cells will be using the same frequencies. If I say the frequency reuse factor is 1, okay, if I say frequency reuse factor is 1 by 3, means out of 3 cells, okay, one will be using the same frequency, other 2 cells will be using different frequencies. That is what. Okay, so here I am using a cluster of size 7, right? I have written here frequency reuse factor is 1 by 7, means only one cell, okay, out of 7 will be using one particular frequency, and this B, cell B will be using different set of frequency. Similarly, cell C will be using different set of frequency, D will be using different set of frequency, cell E, F, G will be using different set of frequency, so that they will not be interfering with neighbor cells. Okay, so with that we can say there will be no adjacent or neighbor cell interference among the base stations or among the users. Okay, either we can use omnidirectional antennas or directional antennas. I will tell what is the advantage in using directional antennas, how we will be able to improve the system capacity and other things. Hope this picture is clear. You will be able to say what is cell. The entire service area is subdivided into smaller geographic area that we call it as a cell, right? Or we can say the area uh, covered by one particular base station is known as a cell. Okay. Yeah. As I was telling, see, this is the transmitter, right? This is the transmitter, and this is my user. Okay, mobile station is there. So as he moves away from this base station, see, this is the received power, so it decreases exponentially, right? It falls exponentially. Similarly, this is another base station. So as he moves away from the base station, the power is decreasing. So this helps us to reuse the same frequency channels. Whatever I'm using here, the same frequencies can be used in this base station also, as long as they are spatially isolated. So I need to calculate what is the reuse distance. Okay, so that is why I written here reuse distance. Okay, so this is a cell radius which I denoted by R. Fine. So an efficient way of managing the radio spectrum is by reusing the same frequency within that service area as often as possible, right? So this frequency reuse is possible with this propagation properties of the radio wave, right? Okay. So this cellular systems allows the overall system capacity to increase by making the cells smaller and turning down the power. So more capacity can be supplied by installing more number of base stations. So as the cell size decreases, the transmit power of each base station also decreases correspondingly, right? So here I have given an example saying that if the radius of a cell is reduced by half, right, when the propagation path loss exponent, I will tell what is this propagation path loss exponent when we are discussing about the path loss. So when it is 4, okay, the transmit power level of the base station will be reduced by 12 dB, we say. Okay, if the radius of the cell is reduced by half, and when the propagation path loss exponent is 4, the transmit power level of the base station will be reduced by how many dBs? It is 12 dB, we say. So with that, we will be able to reuse the same set of frequencies in the other cells. Okay. Yeah. So this is just to get a better idea of how the frequency reuse has been implemented and how it can cover the entire geographical area with few number of channels, or I can say with a limited frequency spectrum. Yes, is this clear? The concept of frequency reuse. I said now, the cells which are named by same alphabets are known as the co-channel cells. So this is one cluster. So here I have differentiated with different colors. So this is cluster 1, another cluster, right? So cells which are named with same alphabets are known as the co-channel cells. And those co-channel cells will be at certain distance. Okay. So we need to find out, okay, what will be the approximate distance so that there will be no co-channel interference. Okay. Yeah. So as I said, the cellular system supports user mobility. So that is possible with what seamless call transfer from one cell to other. It has to be provided. Then only we say it has a mobility, right? So which is achieved by the process known as handoff, right? So handoff means what? It can provide a seamless transfer of connection from one base station to another. So providing or achieving a smooth handoff is a challenging aspect in the cellular system design. So small cells will give a large capacity advantage and reduce power consumption. But the thing is, uh, providing handoff, smooth handoff is a challenging task here when the cell size is small. So the drawbacks are, so there will be a need for more base stations, right? As I reduce the cell size, I need to use more number of base stations to cover the entire geographic area. So with that, what I can say is more number of base stations means what? Base stations along with their associated hardware cost will also be becomes more. So as I said, it requires the frequent handoffs also because the cell size is small, right? And with that, even the offer traffic in each cell also becomes more variable as the cell size reduces. That results in inefficiency. So here there will be a trade-off. Okay, so depending upon the requirement, we need to think of the cell size. Okay, yeah, yeah. Just I'm showing here how do we find the co-channel cells, right? So as I said, now the cells which are named the same alphabet are known as the co-channel cells. So here just there is a procedure to find the co-channel cell. Okay, so what the procedure is, we have to move I cells along the chain of hexagons, then turn 60-degree counterclockwise and again move J cells, you will get the co-channel cell. And there is an equation called N. Okay, N is the cluster size, so which is equal to I square plus J square or I square plus Ij plus J square, where I and J are the integers we say. So just for understanding how do we locate the co-channel cell, this is what the procedure is. Just I am giving you extra information to understand this. Fine. Okay. So as I said, uh, co-channels, right, means they will be using the same set of frequencies, right? So we need to determine at what distance if they are. Okay. Then we can minimize the co-channel interference. Right, the performance of the wireless system is significantly limited by the co-channel interference, that we say CCI. So that co-channel interference comes from other users in the same cell or from other cells. Okay, so in cellular systems, actually, other cell interference, right? Other cell interference is a decreasing function of the radius of the cell, as I discussed just in a few slides back, right? Means as the mobile is moving away from the base station, what happens? There will be a exponential decay in the power, right? So that is what I am saying here. A decreasing function of the radius of the cell and the distance to the center of the neighboring co-channel cell, and an increasing function of the transmit power we say. So here to define the co-channel reuse ratio, so which is denoted by a letter Z. Okay, so which is equal to D by R we say. What is this D? D is the distance between the co-channel cells. Okay, it is here shown. D is the distance between the co-channel cells and R is the radius of the cell. Okay, R is the radius of the cell and D is the what? Distance between the co-channel cells. So D by R will give you the co-channel reuse ratio. Okay, if the value of this Z is high, okay, that is the co-channel reuse ratio. No? What happens? The value of Z is high means what? The value of D is more, right? Means the co-channel cells are at a far distance. So with that, what we can say, there will be a reduction in the co-channel interference. I hope you all agree with me. I said the co-channel reuse ratio is what? It is denoted by a letter Z, so which is equal to D by R. What is this D? D is the distance between the co-channel cells. Okay, distance between the co-channel cells, and R is the what? Radius of the cell. Okay, so the co-channel reuse ratio will be equal to what? D by R. And I say if the value of Z is more or high, I can say there will be a reduction in the co-channel interference because the co-channel cells are at far distance, right? Because D is more. And if I reduce the value of Z, means if the value of Z is low, what happens? The distance between the co-channel cells will be less, right? With that, what I can say is the co-channel interference will be increased. So it is a very simple logic, right? So co-channel reuse ratio is defined as what? Which is denoted as Z, which is equal to D by R. D is the distance between the co-channel cells and R is the radius of this cell. So higher value of Z leads to reduction in the co-channel interference, and lower value of Z will be leads to increased co-channel interference, right? Okay, so here we use a term called signal to interference ratio. Okay, so this signal to interference ratio determines the performance of the wireless cellular system. Okay, hope you understand what I am saying. Signal to interference ratio determines the performance of the wireless system. So here performance means it may be in terms of capacity or it may be reliability, right? So how do we define this signal to interference ratio? See, two things are there. One is signal and another one is interference. So it is a ratio of those two, right? So what we can define is it is the ratio of amount of desired power to the amount of transmitted power. Okay, that is known as the signal to interference ratio. Okay, so signal to interference ratio will be determining the performance of the wireless system or wireless cellular system. Okay, so what is co-channel reuse ratio? Which is equal to what? D by R we say. What is D? D is the distance between the co-channel cells and R is the radius of this cell. So higher value of Z leads to reduction in the co-channel interference. Lower value of Z leads to increase in the co-channel interference. So here there is a trade-off with this. Okay, so I said that Z is equal to D by R, which can also be written as square root of 3 into N. Okay, where N is the cluster size, and I know. See, as I said, co-channel reuse ratio is what? D by R, which is equal to square root of 3 into N. Square root of 3 into N means the square root is for both the values, 3 into N. Okay, square root of 3N it is what I can say. What I said, N is the cluster size, right? So for different values of N, I can calculate the value of Z. Okay, so as the value of N increases, the value of Z also increases. So co-channel reuse ratio also increases, right? So here what we need to understand is, I said if the value of Z is high, right? I said there will be less co-channel interference, right? When the value of Z is high, and as the value of N increases, of course the value of Z is also increasing. So when the value of N is high, I say the cluster size is more, right? Yes or no?
Yes, sir.
Yes, when I am saying when no response means what? People are with me or what? Not? Hello?
Yes, sir.
Okay, you are with me. Fine. I was telling here, no? So higher the value of N means what? The cluster size will become more, right? So if N is equal to 7, so I have 7 cells, right? If I say N is equal to 15, then the cluster size is 15, right? So as the cluster size increases, the number of RF frequencies per cell available will become less, right? Yes or no? And obviously, when I have a few number of frequencies per cell, so the amount of traffic handling by the system also reduces, right? So which is not desirable, right? So these things are not desirable. That is why I made here into mark. The thing is, higher the value of N, yes, the value of Z also increases. Yes, that leads to reduction in the co-channel interference. But what is the difficulty? As the value of N increases, cluster size increases. As the cluster size increases, the number of RF frequencies available per cell will also reduces. So as the number of RF frequencies per cell reduces, the traffic handling capacity of the system also reduces. So these things are not desirable one. That is why I made it with into mark, right? So lower value of Z. So when I can have a lower value of Z for small value of N, right? So when the value of Z is less, it leads to what? Higher co-channel interference. So which is not desirable one, right? But when the value of N is small, what happens? More number of RF frequencies per cell is available, right? With that, I can say there will be increased system handling capacity, but which is desirable one. So here there is a conflict, right? To make it the frequency reuse as efficient as possible, I need to have a sufficient distance between the co-channel cells. Then only I can avoid the co-channel interference. But what are the drawbacks? Having higher value of Z or having higher value of N. So these things are right, and having low value of Z also have some drawback and also have some advantage. So here there is a trade-off while designing a system. So the wireless system designer engineer has to take care of these things in deciding the appropriate value of Z and the appropriate value of the cluster size, so that both can be maintained. Okay, means by reducing the co-channel interference at the same time able to achieve the high capacity. So let us see how it can be done. Hope you are understanding what I am saying here about the system design trade-off.
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Yeah. Yeah. Okay. Okay. So to just have a mathematical interpretation of this signal to, that is co-channel interference, right? As I said, co-channel interference ratio is what signal to interference ratio. It is given as S by I, right, is equal to desired power, that is S is desired signal power in a cell, to what ratio, that is summation K equal to 1 to Ni Ik. So what is it? Ik is the interference signal power from the kth cell. Okay, so desired signal power to the interference signal power from the kth cell is the signal to interference ratio, right? So where Ni is the number of interfering cells. So how do I know how many cells will be interfering and all? We'll see. Okay, this is what the definition of signal to interference ratio, which we express mathematically. Hope this is clear. S by I is equal to S divided by, what is this S? S is the desired signal power in a cell, and I am writing in denominator summation K equal to 1 to Ni Ik. What is the value of this Ni? I said Ni is the number of interfering cells, right? Okay, so to understand that how many interfering cells will be there in the first tier or second tier and third tier and so on. So here I have taken an example. So this is the first tier, what I say. So this is one central hexagonal cell, right? So around that there will, if I consider this as A, okay, center cell as A, then there will be B, C, D, E, F, G, right? 6 will be there. After that again I have replicated this, right? So here I marked this is the first tier, what I am saying. Okay, so in the first tier how many cells are there? So there will be 6, okay, 6 cells which will be interfering with the center cell, and all these 6 cells will be using the same set of frequencies. Hope understanding what I am saying. And they are all at equidistance from the center cell. Okay, to get this picture clear, let me show this diagram here. Okay. Yes, able to understand here. Okay, of course here 2 more this one cluster size has to be repeated to get that picture clear. So this is A, right? Okay. So and here, sorry, I think, yeah, here another A is there, right? Here another A is there. So here another A is there. Similarly, if I keep another cluster here, A will be there, right? Here another A will be there. Here another A will be there. So how many there? How many A's are there surrounding this central cell A? 1, 2, 3, 4, and here 2 more I need to keep, right? So it will be 6. That we call as a first tier. Hope understanding what I am saying. So those all 6 cells which are named by A will be using the same set of frequencies as the center cell which is named by A. So there will be an interference from those cells to the center cell. Okay, that is what we say in the first tier. Maybe second tier, like that, it keeps increasing. Okay, here it is shown in a very narrow manner. Okay, hope you are getting that idea. And I said from center cell to the co-channel cell is the what distance d, right? This r is the radius of the cell, right? That will give you the co-channel reuse ratio. And as I said, the signal power at any point will be inversely proportional to the inverse of the distance from the source, which is raised to the path loss exponent. Okay, this path loss exponent is denoted by this letter, and usually the value of this path loss exponent lies in this range, that is 2 to 5. Okay, in a nutshell, what I wanted to define is the signal to interference ratio is equal to what? The desired signal power in a particular cell to what? The number of interference signal power from the kth cells. Okay, here I have, as far as this example is concerned, the number of interfering cells in the first layer will be 6. Okay, so we need to take the power from each of these 6 cells, which will be interfering with the center cell, so which is a co-channel cell. The power in this is the desired one, right? So that will give the signal to interference ratio. Okay, so I think I skipped this. It is just told in terms of other things. That is the co-channel reuse ratio and radius of a cell, and as well as the reuse distance, co-channel reuse distance. You can just have a look. Yes, any questions to ask with respect to this co-channel interference and frequency reuse concept? Yes, do you have any questions to ask? These things I covered so far. I'll go to the next one. So if you don't have any questions, so the next thing is the sectoring. So why do we go for sectoring, right? As I said in the previous slides, if I use an omnidirectional antennas, it will be covering the cell in all the directions, right? If I use a directional antennas, okay, if I use the directional antennas, still I can improve the signal to interference ratio. So by doing that, I will be able to improve the system capacity. Okay, so here there are two ways to do that. Okay, so one is 120-degree sectoring. Hope you are able to see this. The given cell is divided into 3 sectors. Okay, the angle between those 3 sectors will be 120 degree. So 120, 120, 120, it will be of 360 degree, right? So I can divide one hexagon into 3 sectors. Hope you are understanding what I am saying. 1, 2, 3. So this is with 120-degree sectoring. I can use directional antennas, okay, at the center of this point, so which will cover the each sector. Means 3 antennas which are directed in each sector, right? 1, 2, 3. So with that, I can say I will be able to improve the system capacity and as well as signal to interference ratio. Okay, instead of using omnidirectional antenna, by using directional antennas, I will be able to improve the system capacity. So this is one way of doing it, sectoring. Another sectoring is also possible. That is, instead of dividing one hexagon into 3 sectors, even I can divide that into 6 sectors, each of 60 degree, right? So 60 into 6, it will be 360 degree. So that is why here I have shown 6 sectors. But there are challenges here. As I already said, if means here the coverage area of a sector is small, no? So when the user is moving from one sector to another sector, so there will be a frequent handoff. Okay, there will be a frequent handoff. So that is a challenge here. Okay, so hope this point is clear. Sectoring, one is 120-degree sectoring, another one is 60-degree sectoring. So with 120-degree sectoring, I can do the sectoring of the hexagon with the 3 sectors, each of with 120 degree, right? By installing directional antennas at this cell site, so which will cover the direction of each sector. So with that, I will be able to, as I said, improve the system capacity. Okay. Hope this point is clear. Yeah. Yeah, the same thing I repeated here. Whatever I said in the previous slide for better clarity, what I feel. I think I don't know in the previous slide whether that figure was visible or not. So as I said, we can increase the capacity by using sectors in the cell, right? So that is possible with the use of directional antennas instead of omnidirectional antennas, right? So here one thing I have shown with the 120-degree sectoring. So F1, F2, F3, right? Three sectors. And here I have shown another with the 60-degree sectoring, that is with six sectors: F1, F2, F3, F4, F5, F6, each with 60 degree. Okay, so this is how it looks. Okay, F1, F2, F3 it is a three cell cluster. Okay, here number means the cluster size is 3. Okay, that is why it is written as F1, F2, F3. In the previous example, I have shown a cluster size of 7. Okay, F1, F2, F3 is repeated otherwise, right? So how when I do this sectoring with three sectors, how the frequencies are going to be split, right? See, F1, F2, F3 in each cell. Again, I am going to split with the three sectors, right? F1, F2, F3, H1, H2, H3, G1, G2, G3, and so on, right? So with that, with this means earlier I will be using only three frequencies, right? With a cluster of three, F1, F2, H3 I was using. Now, in the same three cells, I will be using how many? F1, F2, F3, H1, H2, H3, G1, G2, G3. So 3 plus 3 plus 3. How much? 9. 9 different frequencies. Okay. So with that, as I can say, I will be able to improve the system capacity. Okay. So this is just to get an idea how the sectoring, okay, can improve the signal to interference ratio and as well as the system capacity. Okay, so just to give you better clarity compared to this picture, let me show this. Okay, how does this sectoring can improve the signal to interference ratio? So here what happens, instead of using omnidirectional antennas, if I use these sector antennas, right? So only one cell will be, that is one central cell will be experiencing interference from these two sectors, right? With this 120-degree sectoring. Okay, so if I use 120-degree sectoring, okay, in the first tier, right, the center cell will be there and the neighboring six, that is co-channel cells will be there, right? From the six co-channel cells, only from the two sectors, the center cell will be experiencing the interference. So with that, what I wanted to say is the signal to interference ratio has been increased from 17 dB to 24.2 dB. Means if I use the omnidirectional antenna during that time, the signal to interference ratio will be of 17 dB. Okay. If I use this 120-degree sectoring, okay, with that I can improve the signal to interference ratio to 24.2 dB. So how many dBs it is improved? Almost 7 dBs, right? So 7 dB improvement makes the lot of difference in the system capacity. Okay. So this is the picture which is illustrating how 120-degree sectoring reduces the interference from co-channel cells, right? So when I was using omnidirectional antennas, right, in the first tier there will be 6 co-channel cells which will be interfering with the center cell, right? By using sectoring, that too with 120-degree sectoring, instead of 6 co-channel cells, only 2 co-channel cells, okay, are in the first tier will be interfering with the center cell. So with that means I am reducing the number of co-channel interfering cells, right? So with that, the signal to interference ratio will improve. Okay, so by using directional antennas. I don't know how many of you are getting this picture clarity. How do I say that the center cell is experiencing the interference only from 2 co-channel cells, not from any other co-channel cells? Because we were able to see the direction. This is one co-channel cell. This is another co-channel cell. Yes, able to see this diagram. Yes, this is one co-channel cell. See, cells which are named by letter 5. Okay, this is another co-channel cell. This is another co-channel cell that is in the first layer. This is another co-channel cell. This is another co-channel cell, and this is another co-channel cell. Right? This is what the center cell is. Okay, so this is the first layer. Hope you're understanding. So how many are there? 1, 2, 3, 4, 5, 6. Right? There will be 6 co-channel cells in the first layer with the center cell. By using this 120-degree sectoring, so this center cell is experiencing co-channel interference from only these two co-channel cells. Okay, not from any of the other co-channel cells. So it is away from this, no? It is away from these 4 co-channel cells, right? The center cell is not experiencing any co-channel interference from other 4 co-channel cells. It is only experiencing interference from only this and as well as this. Hope you are getting my point. Yes, are you able to understand this?
Yes, sir.
Yeah. To get better idea, I think I have one more slide which will make you, yeah, both with 120-degree and as well as 60-degree cell sectoring which I have shown. So hope I think now the picture is clear. Compared to the previous slide, I think this picture is clear. So this is the first layer what I have considered, right? How many cells are there in the first layer? There will be 6 co-channel cells. So whatever I am rounding now with a laser point. So these are the co-channel cells, right? And this is the center cell. So this is what I say in first layer. There will be 6 co-channel interfering cells. So with the use of this 120-degree sectoring, only this, right, and as well as this will be interfering with the center cell, and this will not be interfering with the center cell. So I am able to reduce the number of co-channel interfering cells by doing sectoring. So with that I can improve the signal to interference ratio. So as the signal to interference ratio improves, the system capacity also improves. Yes, hope this picture is clear. Yes, I am asking you people, are you getting my point? How this center cell, okay, is affected only by this cell and this cell, and not by these 3-4 cells I am saying. Yes, I cannot give you a picture more than this. I think this picture should be able to make you clear how only these 2 co-channel cells will be interfering with the center cell. Why not other these 4 cells, other these 4 co-channel cells? Yes, got my point. Hello, my dear students, please respond.
Yes, sir.
Yeah.
Yes, sir.
See, try to understand, no, because it won't. If you don't concentrate, it will not help you. Right? I am trying to give a picture, very clear cut picture, how by doing sectoring we will be able to improve the signal to interference ratio, and how we are able to reduce the number of co-channel interfering cells, okay, with the center cell. Okay, hope this picture is clear. I said this is the first layer, so there will be 6 co-channel cells with respect to the center cell, right? While doing sectoring with 120-degree sectoring, I said this cell and this cell will be, these 2 are co-channel cells, right? The signal radiated from these 2 will be interfering with this center cell, not with these 4 cells. Okay. Similarly, with a 60-degree sectoring, also I have shown here. Just try to understand with a 60-degree sectoring, what is the improvement? Is it same as 120-degree, or is it less than that, or it is still better improvement? Any one of you can say? Then I can understand that you are with me and you are understanding what I am saying. With the 60-degree sectoring, how many co-channel cells will be interfering with the center cell? Is it possible to say? It's not able to understand this diagram. What I'm saying, what is this then? See here, this with this thick lines, you see, this is the signal radiation, no? Don't know what people are doing. See, this cell is interfered with this and as well as this, right? What about here? Only one cell, na? One co-channel cell will be interfering with the center cell. You're not able to get this point. So this signal will be going in this direction, right? And this is also in going this direction. So only one co-channel cell will be interfering with the center cell. So still there will be an improvement in the signal to interference ratio with 60-degree sectoring. But other challenges are what? I said no, frequent handoff and other things. That is what the difficulty. Yes, hope this picture is clear. Understood? ಏನು ಮಾತಾಡಲ್ಲ, ಸುಮ್ಮನೆ ನನ್ನಟಿ ನಾನೇ ಮಾತಾಡ್ಬೇಕು ಅಷ್ಟೇ. ಎಸ್ಸು ಅನ್ನಲ್ಲ, ನೂನು ಅನ್ನಲ್ಲ. ವಾಟ್ ಇಸ್ ದಿಸ್?